Yeah, hi, I'm Josh Junon. I work at GitButler, and today I'm going to be talking about my journey in making a PCB from scratch, knowing nothing about electronic engineering in the course of 9 months over parts of last year, and how I used async Rust to write firmware for it. So hopefully this is a pretty laid-back presentation. I know you guys have been out here all day long listening to really cool stuff. And here's just a presentation of my trials and errors, many errors, and showcasing a very vulnerable part of myself. So if I'm a little nervous, that's why. Yeah, and in hindsight, moving electrons with Rust, very pretentious title. It's not that serious, but hopefully you guys enjoy it. So yeah, like I said, I'm Josh Junon. I've been writing code. The numbers are different depending on how you ask the question, but professionally for 14 years, but I've been writing code since I was about 9, so it's been a long time. That is my parrot. His name is Lucky, if you're curious. Like I said, I'm a senior Rust developer at GitButler, and I am not an electronics engineer. Just keep that in mind. I'm coming from a very strong software background, right? So yeah, I went from knowing almost nothing about electronics engineering. I had the kits as a kid with the little springs and the stuff, and that was basically it. I went from that to having a fully custom-built board. This is a nice render in Blender, but it does look like this, I promise. To having this, probably very messy to some of you, board in about 9 months, and I wanted to talk about what that process was like. Yeah, if you're an electronic engineer in the room, or if you do automation or embedded or anything like this, you're going to see a lot of weird stuff. Just throw it under the rug a little bit and give me a little bit of slack. Like I said, I'm not an electronic engineer. I didn't know anything about this. The context here is that I'm working on a side project. I won't talk too much about it. But I'm building an operating system from scratch, a novel one. And when you're building an operating system, if you're not sure or if you're not aware of how this works, you usually start with the kernel, which is like the main part of the operating system that kind of manages all the resources and is the supervisor for your machine, right? And building a kernel has a lot of challenges other than the obvious ones, and one of them is testing. Testing and CI/CD, making sure that your code runs on a variety of different pieces of hardware, right? So here's the problem. Booting a kernel requires some sort of your machine that you're testing on be in a boot state. That's not always the case. If you're already running Linux, you can't boot into another kernel. You probably could figure it out, but it's not ideal. Your kernel typically is expecting that it's in a fresh state where the CPU is not fully initialized yet, right? So I can't leverage something like a CI/CD server that already exists, Linux or, I don't know, Jenkins or whatever you want to consider. It kind of goes all out the window because you are the computer. You are testing the kernel, the main part of the computer, right? You don't have any network connectivity at that early on, more or less. We'll kind of get into that a little bit. Doing kernel dev typically means that you flash your kernel onto a USB stick and then physically move that from one machine to another and plug it in and reboot, and your kernel runs, right? If you have 20 different configurations you want to test against, that's 20 times you're plugging stuff into, and it doesn't really scale. And it's also time-consuming. And you have the human element to it, right? So you kind of want to automate this at some point, especially if you're doing CI/CD or you're having contributions from other people, and you want them to also test against this hardware, right? On that note, contributors benefit from having access to all the same CI/CD infrastructure that you have. So the vision that I would have for this project is that if you did a PR against the kernel, you would test it against all of the weird, quirky hardware that exists that we also test against. And that's not something you can get with the USB stick. There's so many different combinations of hardware, and really the crux of it is we have VMs to test kernels in, but VMs give you a very ideal state, right? They work the same way every time you boot them up. They don't emulate all of the weird quirks. If you've ever played like a NES emulator, the NES has a lot of weird quirks that NES emulators don't quite capture, right? It's the same thing with VMs. VMs give you perfect ideal state, but I still want to test against weird combinations of very old hardware or very new hardware or whatever. And you can't really do that just on a single machine. You have to have physical machines at some point in time. And I'm sure many of you are familiar with something similar in that regard. As far as I'm aware, as far as I could research, there's not great, cheap solutions to this. You have things that help you get there, Raspberry Pis and whatnot. But there's no all-in-one thing that handles, like, load the kernel from, like, a GitHub Actions run, pull it down, boot it into the system, talk to it via serial, and then send that back up and have this all as one, like, nice part of your CI/CD pipeline, right? So I took this as kind of a cool opportunity to learn how to do some electronics engineering, to build a board that sits in front of a real machine and then interacts with it over Ethernet, over USB, over serial, all of this stuff. That's the context. That's the background. How was I going to do this? Well, first, I needed a peripheral on the board to connect to my server, right? My server is going to be talking to whatever CI/CD pipeline and serving it images of the kernel to boot. I chose, erroneously, one of my first failures early on, was to choose to do this over Pixie, which, having lots of conversations, it's pretty clear Pixie has some very varied results, especially when you're working with older chips on motherboards where they're very slow. It's not something I want to get into, but believe me, like 30 kilobyte kernel development build took 30 minutes to boot once. So I'm investigating other ways to do this, but at the time, Pixie sounded great, and so I figured another Ethernet port, and I can proxy Pixie stuff to the server and, you know, make this nice little middleman sort of thing. Serial I/O to be able to get output of tests, or to be able to say, run this just one test and tell the kernel that instead of it running every single thing, was a need, so I needed a UART. The power and hard drive access lights and things like this, the power and reset buttons, which are actually signals, they're not like hard switches, so the kernel has to react to those, and I wanted to be able to test that. USB, naturally, and then also be able to control the PSU, the power supply directly, and tell it, hey, cut this off, cut the power, this test's been running too long, see if the PSU is even on, things like this, a little bit more for remote management and error handling and fault tolerance, things like this. And I wanted a nice, fancy OLED display so I could see the status of what PRs are running currently. That was over SPI, ultimately. LED indicators, because I'm flashy. And I2C is great. I hope I said that right. I used to say I2C, and I was corrected very sternly one day. And I also wanted nice lab equipment. I worked at Radio Shack. If you're not familiar with Radio Shack, I don't think it's even around anymore. I think they went under. Anyway, it was an electronics shop in the States, and they would sell soldering irons that were basically curling irons on steroids, and would always fail and cause problems and fires and things like this. So I wanted some nice stuff as an upgrade from what I had as a kid. So I had a little bit of extra money out of pocket to spend on this, and you'll see some of that later. And then also aesthetics. I'm an aesthetics boy. I like when things look nice, and it ended up costing me, as you will see, but that was one aspect to this. So that was the plan, right? So how did I figure out even where to start? Well, there's a number of places. Most of you probably know these already. EEV blog. Raise your hand if you've seen an EEV blog video. Yeah, OK, that makes sense. Great resource. If you've never seen them, even if you're not interested in electronics, they're really fun to watch. He's a really great instructor, very clear, Australian, nice to listen to. Electrical engineering Discord server. Is anyone part of this server, by the way? Nobody? OK, cool. I was going to say hi to people, but very helpful. It's just really nice to have the human element to give you feedback on certain things. Altium has a bunch of really great guides. They try to sell you Altium at the end of them, and they will not stop calling you if you ever try Altium. But they do have great guides, and good resource for that. Google Images for when you need to find reference schematics. Just make sure it's not somebody asking, how do I fix my schematic? Because then you just incorporate someone else's broken schematic and do your own schematic. So be careful with that. And then the last one that has a whole bunch of minefield stuff that I won't get too deep into, but ChatGPT was surprisingly helpful in some cases. So if you need resources on how to start, the brute force trial by fire way like this is a great way to go. EEV blog's probably one of the better ways to get into it. And finally, data sheets. If you just really, really, really need to know the nitty-gritty, or if you don't know what you don't know, data sheets are a great way to learn. Like really, they are very dry, very technical. They have way too many graphs on them that you probably don't care about half the time, at least me as a novice. You guys probably do way more than I do. But they're great resources just to see like what do I not know? What are terms in here that I don't know? Then you Google them, ask ChatGPT, so on and so forth. That's how I kind of got started into this, right? So the first board, and I promise pictures are coming, too many pictures. So the first board, going from having nothing in my hands to having a board in front of me, was surprisingly scary the first time. If you've never done any sort of manufacturing work or sending things off to get produced, it's a little scary. As a software person, you don't really ever have this sort of like process in your toolbox. You don't ever really have to do this, right? So some of the tools that I used, of course, KiCad, someone can correct me at some point, FreeCAD. Mauser is where I got almost all of my parts. I know there's controversy around Mauser. I used Mauser, worked fine. And JLC PCB, same thing, controversy. I don't care. It worked great. If you're starting out, these were relatively easy to use. JLC did yell at me, you'll see in a second, about some of them early on, but that's par for the course, right? So the goal was to just get the concept, get it CAD'd out, figure out what I'm doing in KiCad, how that works, get it to manufacture, get it to me, assemble the stuff, see if it works, and try to get that whole process down pat the first time. And that took way longer than, obviously, successive iterations of that did, right? Learn the tools, tricks, and safety practices. My goggles have been far and away the most life-saving thing. Like, there are a number of times where I flicked components up, and I've heard them click against my goggles, and really glad I was wearing my goggles. So that was important for me. And then get the first bit of feedback. I have a board in my hand, I have a picture of it, I have a schematic, a layout. What do I need to improve on it? How do you even begin to submit this to someone for review? The Discord server really came in clutch there. I could send them all of this stuff, and they could just say, hey, here's a problem, there's a problem, fix this, fix that. It was really helpful there. So if you have a resource like that, if you want a link to the Discord, just let me know. I can give it to you. So here is the first board that I have. It's a little hard to see on here, but if you're an electronics engineer at all, you probably see a number of issues with this. No ground plane, first and foremost. Didn't know what that was at the time. This is how it started out, right? This was just a test. Could I make something that converted a 5-volt standby voltage coming from the PSU to a 3-volt voltage? That's a big deal for having done nothing. Like, this is a lot of data sheets reading. This is a lot of learning how routing works. This is a lot of things, right, up to this point. So this was the first board. It's very, obviously, the aesthetics there. Kind of messy, kind of chaotic, but they're there. And you'll see a recurring theme on all of this. I don't know why I chose to do it this way, but I did. Tip for later, black solder mask, very expensive. Avoid that if you can. And this is what it looked like assembled. These switches, don't buy switches if you don't need switches. They are far and away the most expensive component I have run into, and I wanted the coolest Transformers, mechatronic-looking switches Mauser had to offer, and quickly realized that this was not sustainable financially. So you'll see these, and then you'll stop seeing these very quickly. But this is what it looked like assembled, and it did work, kind of. This was the next revision of that. Learned a lot from the first board. Has a ground plane this time, right? I'm not going to go too deep into what each board does or has, but just show you so you can see pictures. So yeah, things I learned on this round. Ground planes are important. Routing is important. Stop buying expensive, stupid-looking switches that I'm never going to need. They even had like a safety mechanism. None of that was necessary. This is not a consumer product. This is for me. And also, make sure you send all of your stuff, or JLC PCB will cancel your order and tell you how much of an idiot you are. And then you only make that mistake once, luckily. So yes. Here's the next thing I tested. I wanted to see if the indicator lights, again, flashy. I wanted to make sure the indicator lights worked. This did not work. This was the buggiest board that I have ever made. There were a lot of things wrong with it. I learned a number of things from this, a couple of funny ones, I think. Pinless packages are harder to work with when you're terrible at soldering or you're not sure what you're doing with soldering or solder paste or things like this. Learn that very quickly. ESD, so electrostatic discharge, interference, moving your hand over things, that's like real. It's not something that people just worry about. It's something that is part of the process, right? I would wave my hand over this and the lights would change colors, and it was cool, but it was not what I wanted, right? It felt very magical, but yeah, something was very wrong. And also I learned that I squared C, am I saying this right? Am I getting nods? Yes? Great. I squared C, really fun to work with. I personally enjoy it. It's very slow. I know there's a lot of drawbacks, but that was something I learned. Also, size matters. Don't buy parts that are so small that your microscope even has issues picking them up. So here's a MOSFET I bought for that board. That is a 22 gauge wire for scale, which is it's not super small, but it's small enough. I had, so many issues with this. I have lost almost all of them in the process of trying to get them soldered on. They're certainly scattered around, perhaps in my lungs, who knows. I might be part cyborg. But you can see that this is sub-millimeter we're talking about, very, very, very small. Something I could have seen in KiCad if I knew what to look for. I was like, oh, that's a really compact piece. I like that a lot. And it turns out that it was a little too compact. Here's what it looks like on my table. If you can't see it, it's that little black dot. That's what that component looks like. So again, the super messy table coming back into play. You'll see it many times in this presentation. And then the next step I took was to try to make the full board. I was like, you know what, I'm tired of making these little modular things. At one point, I tried to make a fully modular, pluggable thing, and JLC screamed at me again. They were like, this is actually 20 PCBs in one. And I'm like, OK, well, I'm not going to pay that much money. So I just decided to go the full Monty and make the first version of the full board, which was a lot. It was a lot. So to break this down, what you're looking at, you can see kind of the same elements that we talked about in the original plan. We have the two Ethernet ports. We have the RS-232, which is the serial line, the UART, front panel stuff, which was needlessly overcomplicated at this time. We have the power module, where the power is translated. This is roughly the same as the first board. And then the LED indicators, the microcontroller, which is an ST microelectronics, by the way, and an OLED controller. In the top left. So this set of sort of components and set of peripherals remain the same to this day, right? So the next boards you'll see are the same sets of things, right? As a side quest, because I hadn't spent enough money yet and hadn't wasted enough time yet, I also wanted to, if we go back to this, you can see the nice little Oro logo in the middle of the board there with the 3 holes. That's actually exposed copper landing pads, and the goal was to wire those up to the serial wire debug line of the microcontroller. And what that means is that this was basically the way that I did debugging and flashing. And I was like, for the aesthetic, I see people crying in the back. I wanted to make a fancy little programmer that hooked onto the front and used pogo pins and broke my bank account. So I did that and really tried, guys. I really tried, and it just it kind of worked, but it didn't ultimately work, and it was a huge failure. It taught me a lot of stuff, so I guess not fully a failure, but that's what these were. I actually am kind of proud of this. I did CAD all of this out so that you could break apart. I have some with me if you want to see them after the talk. You can break these pieces off and then assemble it into this with the pogo pins and then the little board that you solder onto this that's actually the programmer. And there were 2 revisions of it. Fun fact about this, if you're starting out and don't know this, those little arrows on the right one, that helped me align it because figuring out the alignment was a nightmare. Those little arrows, even though there's no copper or routing or anything on those other ones, since there was any silkscreen, JLC PCB still considered them separate boards. So I actually paid for 4 boards on the right side instead of just 1. So fun fact about that. And this is what it looks like completed. It's right here, the same one. I think it looks super cool. It's not practical at all. It was the biggest headache ever. And you'll see this one for a few more revisions until the very last one where I did an edge connector. It works a lot better. So yeah, all for the aesthetics, costs a lot of money and time, and wasn't super useful in the end, right? Around this time, a friend of mine who's been a big supporter of the project donated an open bench table. If you've never seen this before, it's just like a computer chassis that just everything's open air, really easy to work with. But the cool thing about it is that they had some connectors on the side where you can mount your own stuff if you wanted to, whatever that was. And it's fit typically for fans, like case fans. But I was like, hey, I'm going to actually mount this onto the open bench table because it makes a lot of sense. But the previous form factor didn't make any sense for that. The screw holes meant nothing. I wanted to mount it to something at some point, but I didn't know what. And so the form factor changed a lot. And this is the form factor that is there today. And this was Rev 4, so the last one was Rev 3. I don't remember why I started with 3. Again, aesthetics, I guess. I don't know. So this is Rev 4, and this is starting to inch closer to what I have today, right? So I'm not going to break down where all the components are, but it has all of roughly the same thing. So there's this that fixed almost everything except for the OLED controller, and this is the next revision, second to latest. And then I had the OLED controller, which was a huge nightmare. And the only reason why it was a nightmare, it didn't work for several revisions, I could never get it working, was because I had misinterpreted the connector for the OLED in the documentation upside down. So everything was backwards. I caught 2 OLED screens on fire, and it ran very, very, very hot, and I was drawing as much current as the PSU could take, causing the PSU to preemptively shut off at times. So I was pumping a lot of juice through some very weird, small lines. That was a lot of fun. Have a fire extinguisher on hand. I did not have to use it, but it could have easily been the case. So just invest in one. They're not expensive and very worth it. And finally, we get to the latest revision, which does have the correct OLED controller, and everything else is working fine. There are still some erroneous pieces in here. I added way too many MOSFETs and did not know how they worked until after I made this version, fully at least. So there's some jumpers and things in the final thing you'll see in a second. But it works. It works. After 9 months, I went from watching EEV blog and not knowing what a ground plane was to this, because of resources on the internet, which is a fantastic, beautiful thing because of open source software. This is all done with open source software, which is just, to me, very incredible. I think that's a really cool thing. I learned a whole new skill. I'm probably never going to get a job doing this. For a variety of reasons. One is I don't really want to, but also I'm not certified in any of this, but I did walk home, or I guess come home to my mailbox one day and have this in there, right? So this is what it looks like all set up and populated, and on the thing you can see some of the jumpers there. It does work. I do have videos of it. Here's the back and how everything plugs into the computer. There is a screen there I mounted just for VGA, but it's mostly just to see what it's doing. Here's a nice fancy render of it. Again, Blender, great stuff. I thought I had videos, but I think they're coming after the firmware part. So the firmware. I use Embassy. Raise your hand if you use Embassy. Cool, love Embassy. I was going to wrap my own async sort of thing with like the STM32 crates and the, I guess, Metapack. I don't remember all of these words coming to my head. And it was not very ergonomic. I did try the C, like the basic firmware that gets generated from their toolchain in C. And that was actually part of the chip selection process. In Microchip, for example, I was looking at Microchip chips. It's a company called Microchip that makes microchips, if you don't know. And their tool chain, I downloaded it and generated like just a hello world thing, and it didn't even compile. So I didn't buy a Microchip chip. STM32 was the only one that let me actually log into their website, let me download their software, let me generate something, and actually built it the first time, and had tooling that allowed me to program it. It was the only chip that I could get that far. So I've had very good results with that. Embassy took it to the next level. I was able to build the firmware and get it working with Probe RS. I'm sure many of you know what Probe RS is. Great little tool. This is not my screenshot, but it's a tool that allows you to see what chips are connected to your machine. In this case, it's an edge connector that I have that's a programmer connected to USB, blah, blah, blah. And Probe RS will see if it's there, know how to program it, send your firmware up to it, and then we'll run it, and we'll show you the logging output from it, right? And so these two tools in combination allowed me to go to firmware, to get to firmware in just a couple of weeks, right? It's Rust conference, I have to show a little bit of Rust. So here's some firmware. I really want to show that like a whole network stack with small TCP was available over SPI. It made things very easy for both the system under test USB as well as Ethernet, as well as my Ethernet to the outside world. I'm just showing you that it's all async. I'm running out of time here. Sorry, I'm going to kind of go fast through these. Connecting to everything. Everything just worked. It was amazing. Come to me if you want to actually see the thing. Here's the firmware if you want to go look at it. It's probably not fantastic, but you can go look at it if you want to. Things that I learned, interesting stuff. The code is way more modular, readable, and robust in Rust than the C code, and it was really easy to work with the tools that were provided. I was able to completely abstract away the chip specifics and the pin layouts and things like this, so that if I ever had a problem with actually sourcing more of the chip, I could just substitute it with another one and set up the configuration differently, and it would just hopefully just work. And it also, I think the most interesting one is that since it was an async runtime where there was nothing else happening, and it could just put the chip into a halted state when nothing was happening and it was waiting for an interrupt, it actually ended up using a lot less current and wasn't hot to the touch anymore, which was pretty cool. Yeah. So how long did it take to get to firmware? From Git init to first Pixie boot took me 2 weeks, and I credit that almost entirely to the Rust ecosystem. Which, in my opinion, is pretty incredible. I have done firmware professionally before, and I don't think we could have moved that fast in C or C++. Here's some videos of it working. Yeah. And I do have a tier list here. I might actually skip this, but soldering iron, totally great. Microscope with ears, totally great. Bottles, don't really need them. This is from the perspective of a novice, by the way. If you're a professional, this is obviously very different for you. Table vacuum, awesome, S tier. Goggles, S tier, need those. Saved my eyes several times. Messy shelves, get some shelves, useful. Top of the line multimeter, don't really need to spend $800 or whatever I did on a Fluke, what is it, 87V or whatever it's called. I just was like, best multimeter and bought it, and you don't need that great of stuff. So C tier for a novice, probably S tier for many other people. Messy desk with an ESD mat, which is what I'm trying to show here. Great ESD mat from Weller. Weller is the brand name, right? Weller, thank you. Weller ESD mats, I did have one that was like a roll-up, terrible one before, don't recommend. All of your ESD equipment, you need shitty Chinese power supply, S tier, definitely need this. Heat gun, evil, spawn of Satan. This thing burnt me so many times, and I've used it once, and it was useful the one time I needed it, but haven't needed it since and haven't turned it on since. So don't need that if you're an amateur. You can probably get away with it without it. Skillet with sand. Does anyone know what this is, what I'm doing with this? Yes, I'm seeing some nodding. Yeah, surface mount soldering. You don't need a fancy oven. You need aquarium sand and a 25 euro skillet off of Amazon, and it works just the same, right? This was a trick I picked up on a number of different sites, and they were right. This is all I've needed so far, and it's gotten me really, really far. So S tier for that. Really cheap, works great. What did it cost? Here's just a cost breakdown. A lot of money, and some, and some relationships. Half joking. Total, about 5,500 euro total. If you're on a budget, you can certainly do this without reaching anywhere near this, right? You can probably get away with way less, probably a fifth of this, right? If you're really doing a bigger project to start, right? But that's ultimately what it was. Is this a failure? I don't know. I have some great equipment now, and I've done some cool things with it, so maybe not a failure. Tips and tricks for other noobs. I'm really running out of time. I'm going to go fast. Have a goal in mind, big one, obviously. Have something you actually want to achieve with it. Don't buy things that you don't need, and get your parts first, something I came up with. Getting your parts and seeing that they are the size of a piece of hair before you actually go and do all the boards and everything, it just saves a little bit of cost at the expense of time, of course. But I had lots of time and little cost or little money, so I wish I had followed this. Pay attention to package sizes. Again, can't stress this enough. If it looks small in KiCad, it's going to be really small in real life. Aesthetics aren't everything. Don't use black solder mask because it looks cool. It's also much more expensive than using green. Green, for some reason, is the cheapest, probably because it's in most supply. I don't know. You guys know more than I do about this, but it was for the aesthetics. Good equipment is great, and bad equipment is also great. You don't need amazing stuff to get started, right? This is the last tip. Specify custom stencil size, but not the first time because they send them to you with these big boards, and then you can use those boards for other things. So just another little quick hack. And you don't need the best paste. I made that mistake as well. Final thoughts. We got there. Worth it? Absolutely. Am I better off for it? Yes. I learned a lot about electronics, about microcontrollers, about programming, about interrupts, about all these things that are relevant also to the greater project. This is really a side quest. To the main quest project that I'm working on, super useful, absolutely. Expensive switches, expensive aesthetics? Probably not. Do without it. Would I do it again? Absolutely, yes. So, thank you so much.
Thank you. That was very entertaining. We can have one question before I send you. You had a question last time, so I'm just going to see if there's anyone else who has a question. Not that I don't appreciate your questions, but anybody else? You all are too nice. I'll come back to you.
Just a tiny question. Which STM did you get?
The specific model? Whoa, that's a great question. Actually, I could find it. I might have to do this, but I'll tell you in a second. It's an STM32. I have the exact model, I promise. I'm going to go fast. OS, link, firmware. Oh, I don't have internet. That's a problem. Come ask me afterwards. It's an STM32 F4. I want to say. I don't know if that helps at all. I think that's right. It's either F4 or F7. Probably way beefier than I needed it to be, but it's served me well so far. So yeah.
Awesome.
Thank you guys so much.
Thank you, Josh. One more round.